So in 1969, a car broke 200 miles per hour on a NASCAR superspeedway for the very first time in recorded history. And NASCAR's response, their official institutional reaction, was to make absolutely sure that car never raced again. Now let that sit with you for a second. A car was so fast, so dominant, so overwhelmingly superior to everything else on the grid that the governing body of the sport didn't just penalize it, they didn't just add weight or restrict the engine, they rewrote the entire rulebook to ensure it could never compete again. How does that happen? How does a manufacturer build something so effective that the sport itself has to change to stop it? And more importantly, what does that tell us about the nature of competition, innovation, and what happens when someone solves a problem too well? This is legacy motoring, and I spend way too much time thinking about the intersection of engineering, aerodynamics, and the politics of motorsport. If you're someone who obsesses over the golden era of muscle cars and wants to understand the real story behind the most controversial cars in NASCAR history, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Alright, to understand why NASCAR eventually banned the Dodge Daytona, you need to understand what NASCAR actually was in the 1960s. And here's the thing, it wasn't really a sport, not in the way we think of sports today. It was a corporate knife fight disguised as a weekend at the racetrack, with billions of dollars in car sales hanging in the balance every single Sunday afternoon. The philosophy was brutally simple. Win on Sunday, sell on Monday. If your car crossed the finish line first at Daytona or Talladega, regular working people, guys with families and mortgages and car payments, they walked into dealerships the following week and bought that car, or at least a street version of it. They wanted to own the thing that won. They wanted to sit behind the same steering wheel, feel the same rumble, drive the same machine that beat everybody else on national television. The manufacturers knew this, and they spent accordingly. Ford and Chrysler were the two heavyweights slugging it out week after week. General Motors had largely pulled back from factory-supported racing after a gentleman's agreement in the late 1950s, a handshake deal where the Big Three supposedly agreed to stop pouring money into motorsport after a series of fatal accidents. GM mostly honored that agreement. Ford and Chrysler did not even close. Chrysler campaigned under both the Dodge and Plymouth banners, fielding multiple teams across both brands, spreading their engineering resources and factory support across a wide net. Ford threw everything it had at both Chrysler divisions, matching them dollar for dollar, engineer for engineer. We're talking millions of dollars a year flowing into engine development, chassis tuning, aerodynamic tricks, driver contracts, team sponsorships, and factory-backed operations with the best mechanics and crew chiefs money could buy. These weren't weekend hobbyists tinkering in their garages. These were corporate war machines with racing licenses. And the rulebook? Well, look, the rulebook was more of a suggestion than a law. NASCAR had rules, sure, but they were loose, vague in places, full of gaps and gray areas that creative engineers could drive a stock car through at wide open throttle. The sanctioning body tried to keep things competitive, tried to maintain some semblance of parity between the manufacturers, but the manufacturers had armies of engineers whose entire job, their sole professional purpose was finding loopholes, and they were very, very good at their jobs. The first real explosion in this arms race came in 1964, when Chrysler showed up at Daytona with the 426 cubic inch Hemi engine. Now, the Hemi was a monster, an absolute beast of an engine that represented everything Chrysler's engineers knew about making power. Hemispherical combustion chambers allows for enormous valve sizes and optimal airflow in and out of each cylinder. The design wasn't new. Hemispherical chambers had been around since the early days of internal combustion, but Chrysler's execution of the concept was on another level entirely. The airflow numbers were staggering. The power output made everything else on the grid look like it was running on half its cylinders with the parking brake on. Richard Petty put that Hemi in his Plymouth and dominated. Not just won. Dominated. The competition wasn't close. It wasn't interesting. It wasn't entertaining television. It was one car walking away from the field while everyone else raced for second place. NASCAR's response was swift and decisive. They banned it. For the 1965 season, they declared the 426 Hemi a non-production engine, meaning it didn't meet the homologation requirements for competition. Their argument was that Chrysler hadn't built enough street versions to qualify it as a true production power plant. Chrysler was furious, absolutely livid, and they didn't just complain to the press or file a formal protest. They pulled out. Every single factory-backed Chrysler team left NASCAR for the entire 1965 season. Gone. Empty garages, silent pit stalls. Richard Petty, the king of NASCAR, the most popular driver in the sport, the man whose name was synonymous with stock car racing in America, went drag racing instead. Think about that for a moment. The biggest name in the biggest form of American motorsport was doing quarter-mile runs at drag strips because his manufacturer and the sanctioning body couldn't agree on what counted as a production engine. The standoff lasted the entire season, and ultimately, NASCAR blinked. They let the Hemi back in for 1966, albeit with some restrictions on carburation and displacement rules designed to keep the power somewhat in check. The racing resumed. Petty came back. The fans came back. But something important had happened, something that would echo through the rest of the decade and set the stage for everything that followed. The relationship between NASCAR and the manufacturers had fundamentally changed. The sanctioning body had tried to rein in a manufacturer. The manufacturer had called their bluff, had been willing to walk away from the entire sport rather than accept what they saw as an unfair ruling. And NASCAR had backed down. Everyone in Detroit took note. Every engineer, every executive, every racing director at Ford and Chrysler, and even the guys at GM who were supposedly sitting on the sidelines. The message was clear and unmistakable. Push hard enough, fight hard enough, threaten loudly enough, and the rules will bend. That lesson would have consequences nobody could have predicted. Ford took that lesson to heart. By the late 1960s, their engineers started looking beyond just engine power. Horsepower was important, sure. It was the foundation of everything in stock car racing. But there was another variable that mattered just as much on the superspeedways: air. Specifically, how the car moved through it. How much drag it created as it pushed forward at 180 miles per hour. How much downforce it generated to keep the tires planted on those steep bank turns. How the shape of the body channeled airflow over and under and around the car in ways that either helped or hurt performance. Ford's engineers started reshaping the body of the Torino. They extended the nose, making it longer and more pointed to split the air more cleanly. They tweaked the roofline to reduce turbulence over the cabin. They smoothed out surfaces that created separation points, where air would detach from the body and swirl into energy-wasting vortices. They flushed the grille so it sat even with the surrounding bodywork instead of creating a pocket that caught air like a catcher's mitt. The result was the Ford Torino Talladega, named after the superspeedway where it would compete. Mercury got its own version, the Cyclone Spoiler 2. The changes were subtle compared to what was coming from Chrysler. You could park a Torino Talladega next to a standard Torino and most people wouldn't notice the differences unless you pointed them out. But the engineers noticed, the timesheets noticed. The Talladega was faster than the standard Torino by a meaningful margin on the big ovals. And here's what most people don't realize. It wasn't because of the engine. The same power plant sat under both hoods. The difference was the shape. Ford had drawn first blood with aerodynamics. They had proven a concept that would eventually reshape all of motorsport. You could find speed without adding horsepower. You could go faster without building a bigger engine. You just had to cheat the wind. Chrysler's engineers saw exactly what was happening. They watched Ford's aerodynamic cars winning races that Chrysler's superior Hemi engine should have dominated. And that's a painful realization when you're the company that builds the best engine in the sport. You've got more horsepower than anyone. You've got better torque. Your engine is a work of art that makes a competition look primitive, and you're losing. Not because your engine isn't good enough, but because of the shape of the sheet metal wrapped around it. You can't just add more horsepower. The engine rules are what they are. There are limits on displacement, limits on carburation, limits on what you can and can't do under the hood. You have to change the shape. You have to fix the aerodynamics. You have to find speed in the wind tunnel instead of on the dynamometer. Now, here's the thing about the 1968 Dodge Charger. On the street, it was a masterpiece, an absolute icon of American automotive design. That long hood sweeping back to the A-pillar, the hidden headlights that gave the front end the clean, aggressive look, the fastback roofline flowing into that gorgeous tunneled rear window, the muscular haunches over the rear wheels. It looked like the future. People loved it. Dealers couldn't keep them on the lot. Customers were putting down deposits before the cars even arrived on the transport trucks. And under that long hood sat the 426 Hemi, one of the most dominant racing engines ever bolted into a production car. On paper, Chrysler should have been untouchable on the superspeedways. They had the power, they had the drivers, they had the factory support, and the engineering talent. They weren't untouchable. They were getting beaten. And the problem wasn't what was under the hood, it was everything above it. That beautiful, iconic, beloved Charger body was an aerodynamic catastrophe at racing speeds. And once you understand why, the whole story of the Daytona starts to make perfect, logical, inevitable sense. At normal highway speeds, 70, 80 miles per hour, aerodynamics matter, but they don't dominate. Your engine has plenty of power to push through the air. The drag forces are manageable, you barely notice them. But once you get above 150 miles per hour, the equation flips completely. Drag increases with the square of velocity, not linearly, exponentially. So at 150, you need a certain amount of power to overcome air resistance. At 180, you don't just need a little more power, you need dramatically more. And at 190, 200 miles per hour, the air becomes a wall, a physical, invisible, relentless barrier that no amount of horsepower can brute force through efficiently. Every imperfection in the body shape, every surface that catches air wrong, every turbulent pocket and separation bubble and pressure differential costs you speed. Not a little speed, miles per hour. The Charger's signature design feature, that beautiful recessed rear window, was the worst offender. At racing speeds, air flowing over the roofline would hit that concave glass surface and just lose its mind. Instead of flowing smoothly down the back of the car and trailing off cleanly, it swirled, it detached. It created a massive pocket of turbulent, low-pressure air right behind the cabin that acted like a parachute bolted to the back of the car. Buddy Baker, who drove the Charger in competition, purportedly said the thing felt like it was being pulled backward at Daytona. That's a race car driver at 180 miles per hour telling you the car feels like it's going in reverse. That's how bad the aerodynamics were. The front end wasn't much better. That recessed grille, the one that looked so aggressive and clean and menacing on the street, created massive front-end lift at speed. The air hit that recessed pocket, created high pressure under the nose, and pushed the front end up. The car literally wanted to fly. Not in a good way, in a terrifying, the front tires are getting light, the steering is going vague, one gust of wind from catastrophe kind of way. Chrysler had built one of the most beautiful cars of the decade, maybe the most beautiful car of the decade. And it was also one of the worst possible shapes you could take to a superspeedway. Ford knew it, and they were taking full advantage. So, Chrysler tapped two key people to solve the problem. John Pointer, an engineer in Chrysler's Special Vehicles Group who had a reputation for creative problem-solving and an unwillingness to accept limitations, and Bob Marcel, an aerodynamicist who understood airflow the way most people understand gravity, instinctively, intuitively, in his bones. These two were handed a simple brief with seemingly impossible constraints. Fix the Charger's aerodynamics, make it faster than Ford's Aero cars on the superspeedways, win races, win championships, and do it in under a year, because NASCAR's homologation rules required a certain number of production units to be built and available to the public before the car could legally compete. That meant this wasn't just a racing project. They couldn't just build one prototype and show up at Daytona. They had to design something that could be manufactured on a production line, sold at actual dealerships, registered for street use, insured by actual insurance companies, and driven by regular people on regular roads. And it had to be ready for the 1969 racing season. They had less than 12 months from concept to production, less than a year to design, test, engineer, tool up, manufacture, and deliver 500 street-legal cars that didn't exist yet. And here's the kicker, the part that made the whole thing feel borderline impossible. Whatever they came up with, however wild or radical or unconventional, regular customers had to be willing to buy it. NASCAR required 500 units sold to the public, not built, sold. So it couldn't just work on the racetrack. It had to sell in suburban America. It had to appeal to someone walking onto a Dodge lot on a Saturday afternoon. And as the engineers would discover, that was going to be its own kind of problem. So Chrysler's engineers went to work, and what they came back with looked like nothing anyone had ever seen on a stock car or a street car or really anything with a license plate and a VIN number. The transformation started with an honest admission. The stock 1969 Charger had problems. Not one problem, several. And they were all related to the way air interacted with that iconic body shape at speeds above 150 miles per hour. The tunneled rear window created that massive turbulence pocket. The recessed grille was a wall pushing against the air. The overall shape was beautiful and aerodynamically disastrous. Chrysler's engineering team knew they needed a completely different approach. Not a tweak, not a lip spoiler bolted on in the parking lot before qualifying, not a piece of tape over a body seam. A ground-up aerodynamic rethink of the entire car, from nose to tail, from roof to underbody. Everything that touched the wind had to be reconsidered, and most of it had to change. The first thing they tackled was the front end. The stock Charger's grille was essentially a flat wall with headlights, punching through the air at racing speeds and creating turbulence that affected everything downstream. Pointer's team designed a nose cone that extended 18 inches beyond the stock bumper. This was not decorative. This was not a styling exercise by some designer trying to make the car look futuristic. This was a carefully shaped aerodynamic device made of steel with a fiberglass cap engineered to split the air cleanly around the front of the car and direct it smoothly over the hood, under the chassis, and around the fenders with minimal turbulence. The shape was developed through wind tunnel testing, and every curve and angle served a specific aerodynamic purpose. The result was a dramatic reduction in front-end drag. But just as important, it controlled front-end lift. At high speeds, the stock Charger wanted to get light in the front. The wheels would start to unweight, the steering would go vague, and the driver would start praying. The nose cone kept the air flowing smoothly over and under the car in a way that pushed the front end down instead of letting it float toward the sky. Then came the rear window. And this is where you can see how serious they were, how willing they were to sacrifice aesthetics for function. The Charger's signature design element, that beautiful tunneled backlight that gave the car its distinctive profile, was identified as the single biggest aerodynamic liability on the entire vehicle. So they filled it in. A flush metal plug replaced the recessed glass, creating a smooth, uninterrupted surface from the roofline all the way down to the trunk lid. It completely destroyed the Charger's signature look. From behind, the car lost that distinctive concave shape that made it instantly recognizable. And the engineers did not care, because it solved the drag problem. The turbulence pocket vanished. That invisible parachute that had been dragging the car backward at speed simply ceased to exist. Air now flowed cleanly off the back of the cabin, maintaining attachment to the body surface instead of separating and creating drag. This is where it gets really interesting. Then there was the wing. And this was the piece that made the car look like it had been designed on another planet. 23 inches above the trunk lid, mounted on two massive vertical stabilizers that looked like they belonged on a small aircraft, sat a full-width aluminum wing. The height wasn't arbitrary. It wasn't a designer saying, make it tall because it looks cool. At 23 inches, the wing sat above the car's boundary layer, the zone of disturbed, turbulent air rolling off the roof and trunk surfaces. Lower, and the wing would be working in that turbulent air, generating inconsistent, unpredictable downforce that would make the car difficult to drive at speed. Higher, and it would exceed what was structurally practical for a car that also had to be driven on public roads. The engineers calculated the exact height needed for clean, undisturbed airflow over the wing surfaces. And it also, conveniently, allowed the trunk lid to open without removing the wing, since the struts were mounted to the rear fender extensions rather than the trunk itself. Sometimes engineering and practicality align. Usually they don't. This time they did. Now, here's the thing that really shows you how far ahead of the curve these guys were. Chrysler didn't have a wind tunnel large enough to test a full-size car. Most automakers didn't at that time. So they went to Wichita State University, an aerospace facility, not an automotive one. They were literally using the same methodology, the same equipment, and the same analytical framework that aircraft designers use to test wing profiles, fuselage shapes, and control surface configurations. Except instead of testing a fighter jet or a commercial airliner, they were testing a Dodge, a street-legal V8-powered 4-seat Dodge Charger with a nose cone and a wing. The wind tunnel data confirmed what the engineers suspected but hadn't been able to prove quantitatively. The combination of nose cone, flush rear window, and elevated wing transformed the Charger from an aerodynamic brick into something genuinely slippery. The drag coefficient dropped dramatically compared to the stock car. Downforce became predictable, consistent, and balanced between the front and rear axles. The car was, for all practical purposes, a collection of aircraft principles bolted onto a muscle car chassis and approved for highway use. But Chrysler had one more problem to solve, and it had nothing to do with engineering or aerodynamics or wind tunnel data. NASCAR's homologation rules required manufacturers to build and sell 500 street-legal units of any car they wanted to race. 500 cars. That meant Chrysler had to convince actual car dealerships, run by actual salespeople with actual monthly quotas, to stock these things on their showroom floors. And then those dealerships had to convince actual customers, regular people who needed a car to drive to work and the grocery store and their kids' baseball games, to buy a vehicle with an 18-inch nose cone and a 2-foot-tall rear wing. A car that looked like it had escaped from a science fiction movie and was trying to find its way back to the set. The sales teams were not enthusiastic. Dealers reportedly begged Chrysler to take the cars back. Some Daytonas sat on lots for months, marked down again and again, gathering dust and bird droppings on those enormous wings. A few were eventually stripped of their wings and nose cones by desperate dealers who just wanted to move the metal, selling them as regular Chargers at a discount just to clear floor space and make room for something a customer might actually want to buy. The cars that nobody wanted would eventually become some of the most valuable muscle cars ever built. But in 1969 and 1970, they were just weird. Too radical for Main Street, too aggressive for suburbia, too much car for people who just wanted something that looked normal in the church parking lot. The car looked insane. The engineering was brilliant. The question that hung over everything was simple. Would it actually work on the track? Would all that wind tunnel testing and aerospace thinking and aerodynamic theory actually translate into speed on a real racetrack against real competition? In September of 1969, they got their answer. The Daytona's first NASCAR race was at Talladega Superspeedway, September 14, 1969, and the circumstances surrounding that debut were unusual to say the least. The track was brand new, freshly paved, and it was fast, dangerously fast. The banking was steep, the straightaways were long, and the speeds being generated were pushing the limits of what the available tire technology could handle. And that last part was the real problem. Goodyear's tires were shredding at the speeds Talladega demanded, coming apart, chunks of rubber flying off at 190 miles per hour. And a bunch of the top drivers looked at that situation and made a very rational decision. They boycotted the race. Guys like Richard Petty and David Pearson, guys who had families and wanted to keep breathing, said, "No thanks, we'd like to keep our lives. We'll sit this one out." So the field was thinner than anyone wanted for the inaugural event at a brand new superspeedway. But the Daytona still had to prove itself against whoever showed up. And it did. Richard Brickhouse drove the winged Dodge to victory, a relatively unknown driver in a car that made the win look almost effortless. Some people dismissed the result because of the boycott. They said the field was weak. They said a real test required real competition. That was a mistake, because what happened over the following weeks and months made it abundantly clear that the Daytona wasn't just competitive, it was operating in a different category entirely. On superspeedways, the car was lapping consistently faster than anything Ford could put on the track, not by a tenth of a second, not by some marginal difference that could be attributed to driver skill or setup choices or a slightly better pit stop. The aerodynamic advantage translated directly into multiple miles per hour of raw speed advantage over the best that Ford and everyone else could muster. At Daytona and Talladega, where top speed is everything, where the cars are at full throttle for the majority of every lap, that gap wasn't just an advantage, it was devastating. Ford's Torino Talladega and Mercury Cyclone Spoiler 2 were good cars, genuinely fast machines with their own aerodynamic improvements and strong engine packages, but they were bringing knives to a gunfight. The nose cone and wing on the Charger Daytona weren't gimmicks. They weren't showpieces designed to get attention. They were buying real, measurable, quantifiable speed that no amount of engine tuning or chassis setup or driver bravery could overcome. Then came March of 1970. Buddy Baker took a race-prepped Dodge Daytona to Talladega for a close-course test session. The car had the 426 Hemi under the hood. Same basic platform as the race cars. Not a stripped-out prototype, not some purpose-built land speed machine with a parachute on the back. A stock car on a banked oval. Baker pushed it to 200.447 miles per hour, the first stock car ever to break the 200-mile-per-hour barrier on a closed course. 200 miles per hour. In something that started life as a Dodge Charger, something that looked like someone had welded an airplane nose onto the front and bolted a 2-foot wing on the trunk. Baker later said the car felt stable at that speed. Stable at 200 miles per hour on a banked oval in 1970, with 1970 tires, 1970 suspension technology, 1970 safety equipment. The driver said it felt planted, predictable, controllable. That tells you more about the quality of the engineering than any wind tunnel number or drag coefficient ever could. Now, Chrysler wasn't done. They looked at what the Daytona was doing on the track and thought, why stop at one winged car when we could have two? Plymouth took the same aerodynamic principles, the nose cone, the elevated rear wing, the flush rear window, and applied them to the Roadrunner platform. The result was the Plymouth Superbird, released for the 1970 NASCAR season. Same concept, different body shell, same terrifying dominance. And the Superbird came with a bonus that the Daytona never had. Richard Petty. The king himself had left Plymouth for Ford after contract disputes during the late 60s. He'd been racing Torinos, winning races in Ford Blue instead of Petty Blue. And it was wrong. Everyone knew it was wrong. Plymouth knew they needed him back. So when they showed him the Superbird, a car specifically built to be competitive enough to lure him home, he came back. Petty driving a winged Plymouth was exactly the kind of star power that Chrysler wanted associated with their racing program, and it was exactly the kind of nightmare that Ford absolutely did not need. So now Chrysler had two winged cars on the superspeedways, the Dodge Daytona and the Plymouth Superbird. Two teams of drivers, two platforms, both faster than anything else in the field by margins that made the racing feel predetermined. The Superbird was essentially the Daytona's mechanical twin, born from the same wind tunnel thinking, the same understanding that at speeds above 170 miles per hour, aerodynamics mattered more than raw horsepower. Together, they were suffocating the competition. Ford tried to keep up. They genuinely tried. The Torino Talladega and Cyclone Spoiler 2 had their own aerodynamic improvements, flush grills, extended noses, cleaned up body surfaces, but nothing as radical, nothing as comprehensive, nothing as fundamentally reimagined as what Chrysler was running. Ford's approach was evolutionary. Small improvements, incremental gains, careful refinement within the existing design language. Chrysler's approach was revolutionary. Throw everything out. Start from Aerospace principles. Build the shape the wind wants, not the shape the styling department wants. And at 200 miles per hour, evolution loses. So now NASCAR had a serious problem on its hands. The winged cars weren't just winning races, they were making the rest of the field look like they were running a different series entirely. And NASCAR does not like it when one manufacturer dominates. It's bad for television, it's bad for ticket sales, it's bad for the other manufacturers who are also writing checks. And most importantly, it's bad for the illusion that any given Sunday, anyone can win. Let's talk about what actually made this car so fast. Because it wasn't magic. It wasn't some mystical quality that defied explanation. It was math. Pure, elegant, ruthless math. And the math is where things get genuinely fascinating. A stock 1968 Charger had a drag coefficient of around 0.388. For a street car in the late 60s, that was fine. Normal. Unremarkable. You're driving to the grocery store at 55 miles per hour. Nobody cares about your drag coefficient. But at 180 miles per hour, air isn't just something you drive through. It's a wall. And that 0.388 meant the Charger was spending a massive percentage of its available horsepower just shoving air out of the way. Power that could have been going to forward speed was being wasted fighting an invisible enemy. The Daytona brought that number down to approximately 0.28. Here's what most people don't realize about what that number actually means. That is a 28% reduction in aerodynamic drag. For context, Ford's best aero effort, the Torino-Talladega, came in at around 0.32. So the Daytona wasn't just a little better than Ford's answer to the Aero wars. It was in a completely different league. Now, here's why that drag reduction matters in real, tangible, race-winning terms. At 180 miles per hour, that 28% reduction was worth roughly the equivalent of an extra 200 horsepower, without touching the engine, without changing a single valve spring or a carburetor jet or ignition curve. Just by reshaping the air around the car, Chrysler had found 200 free horsepower. That's not a marginal advantage. That's not a footnote in an engineering textbook. That is a cheat code written into the laws of physics. The nose cone was the most visible piece of the puzzle. That long, pointed snout managed something called the stagnation point, which is where air hits the front of the car and has to decide whether to go over, under, or around. The stock Charger's flat front face created a mess of turbulent, high-pressure air right at that decision point. The nose cone smoothed that transition entirely, letting air flow cleanly and predictably in all directions with minimal energy loss. That alone was worth about 5 miles per hour at top speed. 5 miles per hour from a piece of shaped fiberglass and steel that weighed maybe 40 pounds. The rear window modification, filling in that recessed tunnel with a flush metal surface, eliminated the separation bubble that had been acting like a parachute. Simple, elegant, effective, worth another 3 to 4 miles per hour. And then the wing. 23 inches tall, mounted on those massive struts looking completely absurd to anyone who didn't understand fluid dynamics. It operated on the same principle as an airplane wing, but inverted. An airplane wing creates low pressure on top and high pressure below, generating lift that pulls the aircraft into the sky. The Daytona's wing did the exact opposite, low pressure above, high pressure below, pushing the rear of the car down onto the track surface with relentless, predictable force. At racing speeds, it generated approximately 600 pounds of downforce, pressing the rear tires into the pavement. That downforce was absolutely critical. Without it, the car's aerodynamic shape actually wanted to lift the rear end at high speeds. The nose cone was so effective at reducing front-end lift and generating front downforce that the car became dangerously unbalanced without a corresponding force at the rear. The wing solved that problem completely, pressing the rear tires into the asphalt, which meant more grip through the bank turns, which meant higher cornering speeds, which meant faster lap times, which meant winning. Pair all of that aerodynamic brilliance with the 426 Hemi sitting between the front wheels. In race trim, that engine produced approximately 550 horsepower. The street versions were conservatively rated at 425, and everyone in the industry knew that number was a carefully constructed lie designed to keep insurance companies from losing their minds and pricing the car out of existence. The real number was higher, probably significantly higher. The Hemi's secret was those hemispherical combustion chambers that allowed for valve sizes that would have been physically impossible in a conventional wedge-head design. Big valves meant massive airflow. Massive airflow meant enormous volumetric efficiency. Enormous volumetric efficiency meant power that made other engines feel inadequate. So, you had an engine making 550 horsepower pushing a car with 28% less drag than anything else on the track. The Aero advantage didn't just add to the engine advantage, it multiplied it. Every single horsepower went further because less of it was being wasted fighting the air. The combined result was that the Daytona was roughly 12 to 15 miles per hour faster than a standard Charger on superspeedways. In NASCAR, where races are decided by car lengths and fractions of seconds, that's not an advantage. That's an embarrassment for everyone else. So NASCAR had to act, and their solution was elegant in the most brutal way imaginable. They didn't ban the Dodge Daytona or the Plymouth Superbird outright. That would have been too confrontational, too obvious, too likely to trigger another manufacturer walkout like the Hemi ban of 1965. Instead, they changed the math. For the 1971 season, NASCAR introduced engine displacement rules that were targeted with surgical precision at the winged cars. If you wanted to run a car with aerodynamic modifications like a nose cone or an elevated wing, you were limited to a 305 cubic inch engine. Meanwhile, every other car on the grid could run the full 426 or 440 cubic inch engines. The math was brutal. A 426 Hemi made around 550 horsepower. A 305 cubic inch engine made maybe 290. No wing in the world fixes a 260 horsepower deficit. No nose cone bridges that gap. You could have the slipperiest shape ever conceived by human engineering, and it wouldn't matter when the car next to you has nearly double your displacement. The result was exactly what NASCAR intended. Not a single team chose to run a Daytona or Superbird in 1971. The most dominant race cars in the history of the sport became paperweights overnight. Chrysler pulled out of factory-backed NASCAR entirely after the 1970 season. Ford followed shortly after. The manufacturer war that had produced the Hemi, the Boss 429, the Torino Talladega, the Daytona, and the Superbird was finished. And here's the part that makes the whole story feel like some kind of cosmic joke. After NASCAR killed the winged cars, the street version sat on dealer lots gathering dust. Only 503 Daytonas were built. Dealers begged Chrysler to take them back. Some sat for months. Some dealers physically cut the wings off and removed the nose cones to sell them as regular Chargers at a discount. Cars that a dealer couldn't give away for $3,500 in 1970 now sell for over $900,000. Some have crossed the $1 million mark at auction. A Daytona is sat in a barn for 30 years, forgotten, covered in dust and mouse nests, sold for $850,000. That's roughly $250,000 for every original decade it sat depreciating. The engineering legacy runs deeper than collector value. The Aero wars prove that aerodynamics matter as much as horsepower, maybe more. Formula One teams now spend hundreds of millions of dollars on wind tunnel time and computational fluid dynamics. Modern NASCAR's next-gen car uses aerodynamic principles that would look very familiar to John Pointer and Bob Marcel. The sport eventually embraced exactly what it once banned. Those engineers were 50 years ahead of the curve. They figured out the future of racing in a university wind tunnel with clay models and tufts of yarn taped to sheet metal. No supercomputers, no CFD simulations, just observation, intuition, and engineering brilliance. So a car that broke 200 miles per hour on a superspeedway got itself banned for being too good. Build something that works too well and the people in charge rewrite the rules so it can't play anymore. Was NASCAR right? That depends on what you think racing should be. A showcase for the best engineering or a competition where anyone can win. The Daytona answered a question perfectly, and its reward was exile. The system wasn't ready for the answer. Drop your take in the comments, and if you made it this far, subscribe. We do this every day.